We're going to start a new lecture, and this time we talk about something very famous. It's called a Bayes theorem. Okay, before we go to this topic, let's do a quick review. We have learned in the earlier sessions, and I think you still remember that. The first one is a complementary events A and B. So if A and B are complementary to each other, then A is the same as not B, right? Because either A or B, and they're complementary of each other. So they add up to the whole sample space, all right? And then P of A plus P of B will be 1. So for example, if A is an event that someone was born in Virginia, because you don't know anybody there, but if you randomly pick up one person, what is the event that he or she was born in Virginia? And the B is he or she was not born in Virginia. So either in Virginia or not in Virginia, that just became the whole space. That's all the possibilities. So in Virginia is the complementary of not in Virginia. So the probability that a randomly selected person who was born in Virginia plus the probability of not being born in Virginia, that add up to 100%. So either A or B, no overlapping, and A and B, they made up the whole space. So that is the complementary events. Now once we know that, I'm going to talk about something interesting. It's called a at least. All right, at least, let's see, if the event A means at least one, which means one or more, right? Or you can use 1 plus to show it. That means one or more. At least one happened. Then the B, its complementary event will be none. Nothing. Okay, so it could be 0 and then 1 and 2, 3, 4 and above. So if A is at least 1, the complementary is none. For example, if a family have, let's say, 4 kids, then what is the probability that they're going to have, there's going to be at least one boy? All right, so at least one boy. What is the opposite of that? That would be no boys, right? It's all girls. What's the probability that you have 4 girls? And then once you find that probability, you just use 1 minus that, and then you're going to get the probability that they're going to have at least one boy. All right. The other way, of course, to calculate the probability of A is to find what is the probability that they get a one boy, and 2 boys, and 3 boys, and 4 boys. It's more complicated. So if you see the situation like this, you probably want to consider, let's look at the complementary. Usually when you see the word at least, at least 1, and then the opposite, none, that's easier. That probability is much easier to be calculated. Okay, so that is one thing that we know. And the other, that's the complementary. And the other quick review is a conditional probability. Probability, now it's a different AB, okay? So forget about this AB. They're complementary to each other. So the probability that B given A, and that would be the probability that A and B divided by the probability of A. So given this thing happened, we just assume this is happening, and then what is the chance to get a B? B given A, that's the P. A intersect B over the P of A. I don't know if you remember that this is the definition of a conditional probability. Okay, now another quick review. What is a P, A, and B if A and B are independent. Then that will be just PA times PB, right? In other words, the PB and the PB given A is the same because either given A or not doesn't really matter. They keep the same probability. So that is what happened when A and B are independent. All right, see PB given A is the same as a PB. So PB multiplied by PA. See, you get a PA intersect B or PA and B. Sounds confusing, isn't it? All right, now let's keep this in mind. All right, I just assume you know that we're going to review, so you're going to see this again and again. Now we talk about something real, which is the Bayes theorem. There are several ways to show the Bayes theorem. The way I like is this: is P A and B, which is P B given A multiplied by P of A, or P A given B multiplied by P of B. You see that here A and B are interchangeable. All right. Well, some book says, because the Bayes theorem is all about, it's a very, very important theorem about conditional probability. So someone says this, okay, someone says P B given A equals P A and B divided by P of A. Okay, this is the same as what we learned earlier, but it's actually, I just didn't tell the name, but that is the conditional probability. That's the Bayes theorem, or P A given B. Whatever is given here after this vertical bar, that is in the denominator, P of B, and the top is P A and B. So either way, you can 1, 2, 3, 4. There are like 4 formulas, but they're exactly the same thing. So every time we talk about a Bayes theorem, so you can just refer to one of these formula to figure out what you need. It sounds difficult. It looks very, very difficult. So you probably have seen here the probability of B given A and the probability of A given B. They're not the same, okay? It's different condition. All right, now we are going to use one example to tell you, I'll give you one example, okay? So, ready? The probability of cancer is 0.01. Okay, this is given. The probability of someone has cancer is 0.1%. Or we know this based on the relative frequency. It seems like 1% of the population has cancer. So P of cancer is 0.01. I can also write a P of C is 0.01. Okay, as a habit, or it might help you because I put a little thing on the right. That is something, whatever I write on the right will help you a little bit. So if I have P of a C is 0.01, then no C, right, C bar, that would be 0.99. Quick review, complementary events. The other way to write that is NC, no cancer. It doesn't matter which way you like. Either way will be work. So every time when you are given some information and you translate that from English to a math notation, and I keep writing whatever I know from that on the right, because that time you don't have to go back and read that again and again. All right, now the second condition is, okay, we know that the 1% of the population has cancer, and the false positive rate is 10%. Do you remember what is the false positive? False positive. False positive. Remember, a guy get pregnant, right? That's a false positive. The test result shows positive, but actually he's not pregnant, or he's not no cancer. So false positive is the probability that the test is a positive given no cancer is 0.1. This 0.1 is the same as this 10%. You see this? Okay, can you translate from this English into the math notation? That sometimes is the hard part, right? So or we can say test positive. Okay, so that's okay. Test positive given no cancer is 0.1. Okay, based on this, what do you know? So test positive given no cancer is 0.1. And then what would be the chance with the same condition, no cancer, the test is negative? These two are complementary to each other, either positive or negative, given the same situation. So that would be 0.9. Sounds good? Okay. Now, with all this information, okay, I'm going to ask you, I give you another one. The true positive rate. The true positive rate is 80%. If the true positive rate is 80%, that means probability test positive given he or she has cancer, it's 0.8. Which means the probability that test positive given C is 0.8, and the test, we know this, complementary events given C, given the same, under exactly the same situation or a given condition, that will be 0.2. See, even I just give you 3 numbers in the question, but you can come up with this 1, 2, 3, 4, 5, 6. You can come up with this 6 probabilities. Okay, so what I'm asking you is, okay, listen carefully. I ask you to find the probability that a subject actually has cancer given that he or she has a positive test result. So what I'm asking is to find what is the probability that someone has cancer given test positive. All right, that's hard. All right, right? It's really, really hard. All right, now we look at this and we think about a cancer, and then we also, something similar like a COVID. Someone has COVID, and the test comes out with some false positive rate, some true positive rate, and I will ask you, what is the chance that the test shows positive, but actually, given this situation, and he or she has COVID, or in this case, what's the chance that he or she has cancer? Looks really, 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 really hard. Okay, so now let's see what can we do about this thing. I want you to keep this in mind. Keep this Bayes' theorem. Probability of A and B will be probability of B given A times the probability of A, and P given A, B given A is the and that. Okay, so we have all the bars of stuff. We can get the and part. Once we have the and part, I need the chance that in order to get this, by Bayes' theorem, the probability of a C given test positive, that would be the probability of C and test positive given the probability test positive, isn't it? Right? But we don't know this. We don't know too much about that. So for C and T plus, C and T plus. I have something here. I have a T plus and a C, and also I have a C. I can get the numerator. Can I? Let me use a different color. In order to find this, C and T plus, I can use this and this. All right, so let me do this little by little. Probability that C and T plus test positive based on the Bayes' theorem. That would be the probability TC. What do we know? We know C. So it's going to be T plus given C multiplied by P of C. Right? So that is, we know this is 0.8 multiplied by P of C is 0.01. So that is 0.008. Very good. We get the numerator. We get the numerator here. Now the chance is, what is the probability that he's going to test positive? All right. Now, let's see, what do we know? If someone has cancer, the chance is, let me just grab a different color. I can use yellow maybe. Sorry, here, yellow. Okay. So what we would know is, we can find what is the probability that no cancer. We need to find that. We need to find this, but the test positive, we don't really know. So the test positive is this. Test positive is actually C and test positive plus probability of no C and test positive. Make sense? Here. Make sense? The probability or the chance someone get a test positive, it could be either C or no C. So we add this too. That's an addition rule. If you remember, that's an addition rule. Now, what is the probability of a C and T plus? By Bayes' rule, it's a that would be the probability of, okay, multiplied by the probability of, we switch that with a C, and here it's a C given T plus. T plus given C, and then I'm going to here's no C, so that would be the probability that T plus given no C multiplied by the probability of no C. I'm sorry, that I should give me more space. All right, now think about that. And what is the probability that a T plus given C? We have it. So that is a 0.8. And multiplied by the probability of C, which is 0.01, plus T plus given NC, T plus given NC. Now you see the benefit of having all the things written on the right side. So whatever you get confused or you want to know, you just come here to take a look and you can grab that. So T plus given no C is 0.1. And then you're going to multiply by the probability of no C, which is 0.99. All right, now this is 0.008 plus 0.008 plus 0.099, and the answer is 0.107. And then this one is a P plus that goes to the denominator. Okay, so I should tell you this. Everything in this area is what we're doing for the denominator here. So the top, we have it. The top is 0.008. Denominator is 0.107. So the answer for this question, the probability that actually this person has cancer given the test shows positive is 0.008 divided by 0.107. Guess what? the chance is C and the T plus 0.008 divided by 0.107, the chance is 0.0748. Do you feel okay about this? Given a test result shows this person has cancer, and what is the chance that he or she actually has cancer? Phew, it's only like a 7.48%. It's not too bad, isn't it? So you shouldn't be scared to death when you see the result that shows positive. That's what it says. So I hope that give you a good understanding, and also you feel better about this. All right. Now again, the whole thing we're doing, I want you to know, first of all, you want to write the Bayes theorem somewhere. Either one, 1, 2, 3, 4, there are 4 formulas. Anyone would work because they're exactly the same thing. And also look at for all the given conditions for the question. For any given condition, you're going to translate what they're saying into this math notation. At the same time, you're going to put whatever they didn't mention. For example, they give you the probability of cancer is 1%, and then you're going to put here the probability of no cancer is 99%. So that will help you a lot. See, like this one was not given, and this one, they give you the test, the false positive rate is 10%. They didn't give you this. See, all the things here, the question didn't give you, but I put it there because that will help me later. All right, so this is in this session about a Bayes theorem. I think that it will help you when you start working on the Bayes theorem question. Okay.